What's up? It's officially SCT week. We have an SCT in the next 2 days. And today's topic is electrochemistry. It's pretty crazy that the week just before the SCT they gave us new topics to study. But thankfully, these topics are light. If you know the formulas and if you know the concepts, it's pretty easy. Not like the other topics. Okay, so let's jump straight into it. And first of all, these are some formulas just like last time, but now we're not going to look at them. Let's move on. Okay, principal reactions in electrochemistry. Let's go down. We have oxidation and a reduction. These are the two types of reactions that take place in electrochemistry. What is electrochemistry? What the hell is electrochemistry? Okay, it concerns, this is the field of chemistry which is concerned with converting chemical energy to electrical and electrical energy to chemical energy. All right, this is how your batteries work, AA, AAA, and all that nonsense. That's how these things work. They work on the principles of electrochemistry. Okay, so now what do we need to understand about oxidation and reduction? Let me tell you what oxidation is and what reduction is. Okay, now oxidation can be defined in a few ways as well as reduction. Let me explain the first way. First way is simple reaction with oxygen, or reaction slash addition of oxygen, and this is removal of oxygen. Simple. It's in the name. Oxidation means addition of oxygen. Reduction means removal of oxygen. Simple. Now, there's another way. To define this in the terms of electrons. Now, for that, I want to teach you a mnemonic. Let's take that. I'm just gonna write here oil rig. Do I have space? Yes. Oil rig. What does this mean? Shit. Oh my god. Oxidation is loss. Reduction is, oh god, gain. What? Of what? Loss of what? Gain of what? It is the loss and the gain of our friend electron. Boom. Okay? The loss of an electron is called oxidation. The gain of an electron is called reduction. I know this is like contradictory. Says reduction should mean reducing, but then but actually means gaining. But that's one way I remember it. It's like, oh, it's the opposite. If reduction means to lose, but it's actually to gain. You get what I'm trying to say? Now, let's get this out of here. And let's understand the third way we can use this. Third way to define is the increase in oxidation. The increase in oxidation number and the decrease in oxidation number. What is oxidation number? How do we find out the oxidation states? All of these things I will explain in this lecture. Okay, so keep watching. Now we have this beautiful page over here, so you can see that it has all the definitions that we will need. Oxidation is the boom 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 and reduction is the boom boom boom. Okay, we have all of that. We have all of it right here. Okay, again, let's repeat this again. Oxidation is addition of oxygen or removal of electrons or increase in oxidation number. Reduction is removal of oxygen, addition of electrons, or decrease in oxidation number. Moving on. We need these. These are like the fundamentals. Again, you can see fundamentals, increase in oxidation. It's the same thing. Oxidizing agents and reducing agents. Okay, let's explain these. Okay. Also, the numbers that I've been referring to, oxidation number is nothing but oxidation state. Okay, that's how I learned it in high school, by saying numbers. That's why I'm used to saying it, but I'm sorry, but it's actually states. Okay, so it states for us. So my bad, states. Oxidizing agent. Let me tell you a simple rule for oxidizing agent, reducing agent. Okay, if an object is getting reduced, okay, if me myself I am getting reduced, that means I'm a good oxidizing agent. Let that sit. If I am getting reduced, I will be a good oxidizing agent. But if I am getting oxidized, I will be a good reducing agent. Okay, I know it's got a lot of contradictory stuff here and there, but just remember, okay, understand, if I am getting reduced, I will be a good oxidizing agent. Let's look at a example. What can I give you for an example? Uh okay, let me give you an example. Okay. Why is this so thick? Get out of my face. Okay. Na plus 1 electron is going to give us Na. Okay. Cl minus gives us no. Cl plus an electron gives us Cl minus. Okay. Over here we can clearly see Na is increasing the number of electrons that it gets. Okay, so this is adding an electron. What did we learn? The gain of electrons is reduction. So this guy over here, Na plus, is getting reduced. Okay, it's getting reduced. That means this is also an oxidizing agent. Okay, over here we can see Cl plus an electron is going to give us Cl minus. Yes, this is correct. Yes. Again, this is what? This is getting this is being added an electron, hence it's being reduced. Hence this is an oxidizing agent. Okay? Whatever. So let's look at the definitions here. Electron acceptor. See? Being accepted an electron. Species is reduced. Means the species which gets reduced are nothing but oxidizing agents. Reducing agent is the same thing but opposite. Electron donors, species is oxidized. Understand? Okay, I hope it's easy. It's easy till now. Okay. Moving on, oxidation states. Oxidation state of an atom in a free element is 0. Total oxidation states. Nah, we don't need this. It's okay. This page, it's not a bad thing if you remember it. Of course, it's not. Okay, but I don't think you need it. Okay, let me explain why. Balancing oxidation reduction reactions. I will teach that. This is just, we don't need it. Okay, oxidation numbers. Let's I have a question here. I'm gonna explain it to you in my way. Okay, we're gonna talk about something called half reactions. Okay, half reactions, and we're gonna do them right now. Let's do them right now. uh okay, Now, what we're looking at over here is just finding out the oxidation numbers. Okay? How do we find out the oxidation numbers? We need to know the oxidation numbers of two atoms. Okay? No, not atoms. Yeah, atoms. That is oxygen and hydrogen. We need to remember these two. Okay? Oxygen has a oxidation state of -2. Okay? You have to remember this, -2. While hydrogen, H plus, we know it's got 1. +1 is the oxidation state. Okay? Why? Let's look at this now. Now, when we look at a reaction like this, okay? What do we see? We see that there's no +2 or +3 or +1 or just plus anywhere in the reaction. Okay? That just means that their oxidation states are 0. Okay? This is 0, this is 0, 0, 0, 0. Because if it had an oxidation state, it would be written Na plus, that plus is nothing but the oxidation state. Cl minus, that minus is nothing but the oxidation state. Okay? So now, they're all 0. Let's find out the individual oxidation states. Okay? Now, elements like Cu, H, F, He, keep saying carbon. Any element which is in the singular form, just as C or like Cu or gold or silver, Ag, like that. Okay? Or mercury, Ag, just like that. If it's a single element, then always the oxidation state will be a big fat 0. Okay? Even for elementary molecules like let's say F2, Br2, H2, N2, okay, all of these, they're composed of one type of element. These also have the oxidation state 0, 0, 0, 0. Okay? Okay? So now already we know that for N2, the oxidation state is going to be 0 because it's an elementary molecule. And also the same applies for Cu, okay, which is also an element, so it's going to be 0. But now let's look at water. Water is not an elementary molecule. It consists of two types of atoms, H and O. Now, what we know, what do we know? We know that O is -2 and H is +1. Okay, so let's write that down. Let's write for H, okay, it's +1, and for O is -2. Okay, now we have two of these H, so since H2 will be +2, correct? Understand what I'm trying to say? If it was H3O, it would be +3. Okay, but we don't have that right now. Now, we know that the addition of these both should equal to 0. Because the final oxidation state is 0. Okay? How do we know that it was 0? Because nothing was written on top of it. There was no plus, there was no minus on top, there was nothing on top. So we know that it's 0. So, this is pretty simple. H2 is a pretty simple molecule to understand because we know the oxidation states of O and H. O is -2 and H is +1. So H2O cancels out. +2 -2 cancels out and we get a 0. But let's say we need to find out the oxidation level for Cu over here. You might say, oh, Cu is an element, so it's going to have 0. But see, elements which are alone have the oxidation state which is 0. But when they're with someone, then they have an oxidation state. Okay? So let's calculate for now, we are sure, let's remove all of this. And for now, we are 100% sure that N2 and Cu are 0, 0. Let's find out oxidation state for CuO. Cu and O. Now, looking at the formula, we know that the final oxidation state is going to be a 0 because there's nothing on top, right? So, whatever their individual, whatever over here, their oxidation states are, whatever they are, let's say, we know that they will add up to a 0. Okay? Because that's the final oxidation state. Understand? So, for oxygen, we already know. We know this one. It's -2. That's why I say you remember oxygen and hydrogen. Then the other one you can find out. So now we know that one of them, that is, we don't know for Cu, okay? Please remember again, we know that Cu is an element, but it's not alone here. If it was alone, then obviously it would be 0. But since it's with someone, it's gonna have a charge. It's gonna have a oxidation state, okay? So let's find that out. How do we find it out? We know, let's consider this oxidation state to be X, okay? We know that X plus -2, that comes from here, will be equal to, that comes from here, 0 total state. Bring it up, X is equal to +2. Boom. So X over here, the charge over here will be +2. That's how you find the oxidation states, okay? Let's do that again, but over here now we'll use NH3, sorry. Let's go. Now, let's start all over again. Looking at the formula, looking at the equation, what do we know about NH3? What is the oxidation state of NH3? I hope you said 0, because there's nothing on top. Again, there's no +1, there's no +2, there's no minus, there's nothing. Okay? So that's how we know that NH3 is at the final oxidation state is 0. Now, let's split them up. HN and H3. Since there are, now let's look at the oxidation states. Okay, we don't know what they are, but we know for one, we know for H. For H, it's +1. But is this right? I hope you said no, because we have 3. We have 3 H's. Okay, we have 3. That means it's going to be +1 plus +1 plus +1. That's 3 plus 3. That's the charge right there. Let's consider N to have oxidation states of X. We know that X plus 3 will be equal to, coming from here, 0. So X is equal to -3. So the charge of N over here in this particular situation is -3. I hope you guys understand how to find out the oxidation states. Understand? Because mostly, I said you need to remember oxygen and hydrogen, because mostly they're going to give you elements or molecules which contain O and H. So it's going to be easier for you. Mostly, okay? So that's why, please remember, oxidation is a big fat -2 and H is a big fat +1. That's how we figured out, and you can see over here that we were spot on, -3 +2, all of that. Okay? Let's move on. Balance the following reaction. Okay, now we're going to talk about half reactions. Okay, very important topic. Please listen. Half reactions. Okay. Now, every redox reaction, when you're talking about redox, we mean that reduction and oxidation takes place at the same time. Okay, let's kind of look over here and see where's the oxidation happening and where's the reduction happening. Okay, I2 becomes I minus. Okay, which basically means that it has accepted an electron. Gain of electrons is, I hope you said reduction, because it is reduction. Over here, H2S becomes H plus. At S, I know, but let's just look at the H over here. H going from a 0, complete 0 state, goes to a +1 state. That means it has lost an electron, and losing electron is oxidation. So we can clearly see that reduction and oxidation take place in this. So this is a redox reaction. Now let's write oxidation and reduction as separate equations. We know that this is happening, but we know that in this equation we have a oxidation part and we have a reduction part. So let's write it like that. Okay, let's write it like that. I'm first going to take I2. Let's just take I2. Okay, let's just take I2. I have I2 here. Okay, we know that we need an electron. Okay, we need an electron. So giving an electron, let's just write what we have over here. Remember, I2 gives I minus. Already we can see that there's two i's over here and one I over here. So to balance it out, we write a 2i minus. Understand? Now, what do we add? Then we add another thing. Now we see over here that 2i minus. 2i minus. I minus, basically minus 1 is what I minus means. And minus 1 basically means that there is one extra electron. But since we have 2 now, because we added the 2 to balance, now we have 2 electrons. Okay? But we don't write them. But we know that compared to this side has 2 more electrons. So to balance that out as well, we add on this side plus 2e minus. Understand? Now this is a balanced half reaction which represents the reduction half of the equation. Okay? Now, let's look at H2S. H2S, we can just split them, keep some space between the arrows, and we're just going to write S plus H plus. Already we can see very clearly that H plus, there's 1 over here, there's 2 over here, so balance that out by writing 2H plus. Okay, done that. Okay, S and S we don't need to worry about. I just said ace, that's crazy. S and S we don't need to worry about. Okay, let's bring this guy. Let's bring this guy here. And let's cut this guy out. And let's bring these guys here. Boom. Now, let's compare them again. Okay, we see over here 2H plus 2H plus is basically plus 1, but it's 2. That means the overall charge over here is plus 2. Okay, so now what do we understand? We understand that this side has 2 less electrons. Because there are 2 less electrons, we get a plus charge. Understand? I hope you're understanding this. Okay, so just like over here how there was 2 minus and we understood that there were 2 more electrons, for the plus it's just the opposite. If we see 2 plus, that means that it has 2 less electrons. So what do we do with the place which has less electrons? We add our electrons here. Let me just move this guy here. Plus 2e minus. Why 2? Because 2H plus. Why did I add 2 to H plus? Because H2 to balance it out. Okay, I hope you understand, guys. This is one half reaction. I'm gonna write more, so I hope I'm gonna write more so you guys understand more. So this is just one of them. And now what we have done already in the process of writing these equations, this represents oxidation. Sorry, let me just write that down. In the process of writing these 2 equations, we have balanced them out as well, right? This is what we did. We balanced out by adding 2 over here, 2 over here, electrons over here, electrons over here. Now what do? We write them both down. We write these 2 reactions. The first reaction, the second reaction down like that. I2 plus 2 electrons gives 2I minus, and then H2S plus nothing plus, so that just gives us a S plus 2H plus 2E minus. Okay, do we see anything common here? Yes, we do, and that is the electrons. Cut those bitches out. Okay, remember, you can only cut stuff, cross them out, if they are on the other side of the equation, this side and that side. Okay, you cannot cross out if they're on the same side of the equation. Understand? Yeah. And if you have electrons on the same side of the equation, like over here also you wrote 2e plus minus, that's how you know you're fucking wrong. Okay, now so looking at that, let's look at this. Now we add both of these equations up. We add them up. How do we add them up? Of course, we have removed the 2 electrons, cancel them out. So we have now I2 plus H2S gives us 2I minus plus S plus 2H plus. Beautiful. Now this is the equation that I have written. Is it correct? Let's check. Of course it's correct. Of course it is. See that? It's correct. That's exactly what we got, guys. Okay. So that is how we solve one of the equations. Now, let's talk about voltaic cells. What is voltaic cell? Voltaic cells slash electrochemical cells. That's what they're called. Okay, so see. Electrochemical cells convert chemical energy to electrical energy. Okay? Let me add that again. Chemical to electrical. We do a few reactions and that results in giving us electricity. Okay? Now let's look at this. This is the most simple form of an electrochemical cell and it's also famously called the Daniel cell. Don't know why it's called that, but it's called that. Okay? Now, what do we see here? We see that on the left side we have our anode. Okay? And on the right side we have our cathode. Okay? Oh, sorry, I'm very sorry. Okay. So basically the whole idea of this thing is that these guys, this plates will dissociate into its ions, form a circuit and start running to produce electricity. That's the whole point of this, okay? And this is something called the salt bridge. We use the salt bridge to maintain the circuit, to complete the circuit. If this wasn't there, this is the circuit, right? But if this wasn't there, then this would just be this. What about this area? It's not even there. It's no movement. Okay, something. Now, let's remember a few things. Let's make it easier to understand electrochemical cells. We have a mnemonic lone. Lone. What does lone mean? Let me write it in a different way. Lone. Lone. Lone means left. Oxidation. Anode. Negative. Has everything you need to know. You could honestly just remember this and forget the next mnemonic I'm going to teach you. Left side. On the left side is going to be the anode, which will undergo oxidation and which will be negative. Now, just have a bit common sense and think what it's going to be for the opposite. On the right side, you're going to have the cathode, which will undergo a reduction and which will be positive. Simple. But I have another one for you guys. Stupid guys. Okay, I'm sorry. That is a red cat. Reduction takes place in the cathode. Reduction in the cathode. That's red cat. Okay? Now, left and right. What do I mean? If I say left and right, but I want to show you an example. Let's say, yeah, this should work. I don't know for you guys if this is the left or the right. Okay? But I'm guessing if you're watching the video like this, then this is the left and this is the right. Left and right. Okay? Now, that left means this has the anode and this has the cathode. Now, what they do, like I've seen these sneaky guys, okay? I've seen some seminar slides where they show the image like this. Clearly, the anode is on the right and the cathode is on the left. Okay? And then they'll tell you write the cell notation. Okay? Sneaky guys. They'll tell you to write the cell notation. If you don't study, you're gonna be like, oh my god, the anode is on the right side. What the hell am I gonna do? They're just fucking with you. They know that. So when you're writing the cell notation, and I'll teach you how to write cell notation always on the left side, no matter what, you write the anode. And on the right side, you write the cathode. Okay, I'm going to show you as well. They've done it many times. I'm going to show you. Let me just keep these back. Okay, stop recording. I hate this. So yeah, shut up. Let's talk about that now. Let's talk about the standard hydrogen electrode. What is the standard hydrogen electrode? Basically, there is something which you're going to learn now called reduction potential. That is the tendency of a metal or a material to attract electrons. Understand? The tendency of a material to attract or gain electrons. Reduction potential. And we want to measure this value for different metals like copper, zinc, Ag, etc. Now, we want to do that. But how do we do that if we don't have a standard value which we can compare to? Okay? Who said we don't have that value? We do have that value. And that value is the standard hydrogen electrode, also known as SHE. Okay? What is a standard hydrogen electrode? Standard hydrogen electrode has the reduction potential of 0. So we can take this as a baseline to measure the electrode potentials or reduction potentials of other metals. Okay? Remember, reduction potential and electrode potential. Reduction potential is equal to electrode potential. They're the same thing, they're interchangeable words. Okay? Okay? Moving on, we're gonna see this now. See over here we have our SHE, H, which is 0. Now let's understand this. E naught, also known as electrode potential, but like I just said, also can be called as reduction potential. Now I clearly explained that the gain of electrons is called what? I really hope you said reduction. If you would have said oxidation in front of me, I would have slapped your face. But I hope you said reduction. And clearly, gaining electron means reduction. So, this value, E naught, this value over here, E naught, as it gets positive and larger, means that that object will get reduced more. Understand? And as we go lower and negative, that means it's gonna get oxidized more. Okay, understand? This value, again, I'm gonna tell you again, this E naught value, also called reduction potential. Okay. Now, this value, this guy over here, 2.87, very high value, positive value. So we know that it's going to get reduced. Now, if it's going to get reduced, I taught you that people who get reduced are called as oxidizing agents. And people who get oxidized are called as reducing agents. Boom. So just now you're gonna just understand the chart. See, it says over here. Over here it says stronger oxidizing agent as we increase the value, because we know that this is gonna get reduced more. Reduced more equals oxidizing agent better. Okay. That's the whole thing. If you see that there's a high positive value, we know that okay fine, this material it gets reduced. That means it gets added, it adds electron on itself. Okay, so basically it's going to be a good oxidizing agent. And there's another simple way to understand this, okay? Reduced means that you will gain electrons. It's right. It's gonna gain electrons, right? So when I'm getting reduced, I add electrons onto myself. So let's consider this calculator to be an electron. I add it onto myself. Now I'm reduced. Oxidation means loss of electrons. Okay? So it just makes sense. After I get reduced, I'm in the most prime state to be oxidized because I can remove these electrons back. It's only when I have the electrons that I can lose them, right? So that's why when an object is reduced, by that I mean electrons are added, it becomes a good oxidizing agent because now it has electrons to lose. You can think of it like that as well, or just think if it gets reduced, it's an oxidizing agent. If it gets oxidized, it's a reducing agent. Which species will be oxidized? Okay. Over here, see, look what they've given us. They've given us the values over here, E and E. Clearly, we can see this is greater than this. Clearly, that means this is going to get more reduced. Okay, that's it. And this is going to get, if this is see, if we have two guys in an equation, we know one is going to get reduced and other one's going to get oxidized. So if we're looking at the values, we can say that this is going to get reduced. Then obviously this is going to get oxidized. Khalas, just like that. Khadam. Fe plus is reduced and I is oxidized. Boom. And these are just a half reactions which I just taught you. Okay. Standard notation for this is what I'm talking about. The notations. See, left anode, oxidation, lone. Just remember lone. Left oxidation, anode, negative. This is how you write it. You write Zn slash Zn2 plus slash Cu2 plus slash Cu plus. Now, over here you can clearly see 2 electrons are being removed, hence giving it a 2 plus charge, means oxidation. And 2 electrons are being added over here, giving it a 0 charge. That basically means reduction. Okay, so this is happening, we can see over here. But it's a very important thing to remember. When they give us the reduction, again I'm writing over here, reduction potential is equal to electrode potential. When they give us the values for reduction over here, look at this question over here. They said that the standard reduction potential is minus 2.04 for Na plus Na minus, Na plus Na and Zn2 plus Zn. Looking at this annotation over here, we will think, okay, they're both getting reduced. You see, they're both getting reduced. And they are, according to this, they are getting reduced. But see, when you write the value of the reduction potential, the values will always be given like this. They will always be given in the form where they are being reduced. Understand? But it's you who has to put your brain into it and think that, okay, this is greater, this is more or less compared to this. Okay? If it's lower, that means, what did I say? If it's lower, it gets more oxidized. That means this will get more oxidized than this. Hence, we know that this is going to undergo oxidation and this will undergo reduction. I know Zn2 plus slash Zn looks like it's a reduction, okay? But no, this is just how they write the values. This is, you cannot write the electrode potential by writing, you see, this is like a law, okay, which you cannot break. You cannot write E naught and then write Na slash Na plus is equal to whatever number. You cannot write this because this implies that it's being oxidized. But the name of the value itself is reduction potential. Understand? So what I'm trying to say is they are going to give you in reduction. They're going to say like, this is going to give you like this. But you don't look at it and be like, oh my god, that's reduction. What do I do? Both are reducing. No. Use your brain and be like, okay, fine. Okay, fine. This is a lower in value when compared to this. That means that this will get more oxidized. Okay. Hence, this will be the thing which undergoes oxidation. Look at that. Cell notate it now. You know this is going to be the oxidation half, so write Na slash Na plus slash slash Zn2 plus slash Zn, because we know this is going to be the reduction. This is how. Write the cell notation, and that's how you do it. Okay? And then they're asking also for what? Reduce half reactions. Now looking at this, let's look at this. Na, and let's arrow Na plus. Plus 1 basically means that it has one less electron than this side. There's nothing to do, just add one electron here then. Basically this will be the formula. Na gives Na plus electron minus 1 electron minus, and we have Zn2 plus. Let's look at the Zn2 plus. Let's add Zn2 plus, write the Zn2 plus, write an arrow, and write Zn. Over here we can see it's 2 plus. That means it has 2 less electrons than this side. Bro, I'm emphasizing this shit so hard because I understand, it can be hard for some people. So just add those electrons to balance it out. 2, 8. Khalas. See? I'm always right. Now comes E cell. They're going to ask you the value of calculate E cell. E cell. That means the EMF. Okay, let me just go here and show you what the EMF is. Electromotive force. This is the lecture slides. Where is that? I literally just saw it. I'm sorry. Yeah. Electromotive force is basically EMF. EMF, electromotive force. Now you will think, oh, it's force, so it's going to be measured in newtons. No, you'll get 0 for that. It's called electromotive force, but it's a voltage. The value of EMF represents a voltage. I know there are so many contradictory things in this lesson. I know it's hard, but it's like that. What can we do? It is what it is.
Okay. There are two questions that I didn't explain to the best of my potential, so I want to just explain those again. What the hell? Sorry for that, 1 second. Yes, okay. So this question, basically, at the end, I didn't explain this portion of it. So basically, I told you the formula for finding the E cell will be E naught cell is equal to E cathode minus E anode. And I hope you remember that I implied that if one of the values is lower, that means this is the value which is going to get oxidized. And we know that the value which gets oxidized is on the left, which means it's on the anode. So we know the values for both of them, minus 2.714 and minus 763. We don't need to change the values or anything, just use this formula that I have given you. And what do you get? You get E cathode will be, cathode over here is this side on the right. So this is the cathode. So this value we know it's here. The value would be minus 0.763 minus E cell is that much, minus 2714. During this you can do sign conversion and stuff, and you'll get this, and the value will be that will be E cell. That's how you find E cell. That's one question. And one question I totally cut out because when I was solving that question I totally blanked out. I didn't know how to solve it, so I messed up the whole thing and I was waffling for a solid 5 minutes. Where is that question? This one right here, yeah. This one right here. Balance the following question. Now this is, I think, the highest level of the questions you can get for this. So let's see. Let's write the half reactions for this. Now, the confusing bit over here is that there are 2 BRs, but there's only one BR2. That shouldn't be confusing because when you're writing the half reactions, BR minus at the end, we write Br2 here also, and for BrO3 minus, we write Br2 also. And just write it two times, just do it twice. Now, let's see the balancing part. Now, write them down like that as they are in the equations, okay? Then start balancing. You see there are two BRs over here. That means you add a 2 over here to balance that out. Then you see that this is a BR minus, okay? And now since there are 2, this makes it 2 minus. The overall charge here is now 2 minus. Basically, it means that there are 2 more electrons on this side than this side. So we balance that out by adding 2 electrons here. So we add plus 2e. Now, this side has a minus 2e charge, and this side also has a minus 2e charge. Minus 2 charge. Because we know Br2, since there's nothing written on top like this is going to be 0 charge. Okay? Now, let's look at this part now. Again, we see there are 2 BRs here. So we do the same thing and we add 2 BRs here. Okay? Now, we have balanced the BRs. But then there are O's as well. There's O3. And now since we've added 2, it's going to be 2 into 3. 2 times 3, which will be 6 O's, which you have to balance out. Now, when you're balancing out oxygen, this is a little bit different and a little bit hard. We add water instead of adding straight up O's because we can't add oxygen straight up, but we can add water to an equation, right? But we can't add, as I said, oxygen straight up. So we add H2O, but since in H2O we have only one O, and over here we have 6 O's, we just add 6 H2O. Okay? But when we do this, we have to balance another thing. Now this side has 12H more than this side. So we just add on this side 12H plus. Now the whole thing is balanced out. Okay, so we have 12 H's here, 12H here, 6 O's here, 6 O's here, 2 BRs here, 2 BRs here. Now, at the end of the whole thing, you look, okay, are the charges on both the sides balanced? We're going to look at that. And if we see over here, according to this, we know that the complete charge of BrO3 is minus 1, because that's what's given, minus 1. But now since we have 2 BrO3s, the charge over here will be minus 2 for that. So let's run the charge for this is minus 2. And the charge for this 12H plus is obviously going to be plus 12 because H plus is just one charge. So plus 12. That means the overall charge is going to be 10 plus 10. Okay? Plus 10 is the overall charge here. Let's look at this side. Since Br2 has nothing written on top, this is going to be 0. So that's 0. And over here also it's going to be 0. Because 6H2O, I get it. But there's nothing written over here on top. There's no H2O minus, there's no H2O2 plus, there's no H2O2 minus. Nothing like that. So this is 0 as well. So now you can see that there's a charge imbalance. These both have 0. There is a charge imbalance. This has a plus 10 charge. And this has a minus, it has a 0 charge. So what we do is, if we add 10 electrons on this side, it's going to cancel out and make this 0 as well. Understand? You might think, oh, we can just add 10H plus over here. But then if we do that, we have to add 10 over here as well. Then it's going to mess up the whole thing, okay? Just instead of doing that, what if we just move this to the side, cut these out, move this to the side as well, and we just add 10 electrons. Boom. Now we know that the charge of this is plus 10. Now because of us adding 10 electrons, it's basically cancelling out, okay? Because it's going to be plus 10 and minus 10, that's going to be 0. So now the charge here is 0 as well, and the charge of here is 0 as well. So this is our final balanced equation. Now let's look at this now. Now when we add these equations, we can't cancel out the electrons because there's 2 here and 10 here. So what we do to this equation is we take this whole equation, the whole thing, and we multiply the whole thing by 5, just because we want this number of electrons to become 10. Then what we get is we get 5 2 is a 10, 5 times 2 is 10 Br, then we get 5 Br2, and then finally we get what we wanted, 10 E minus. So we got that, okay? I know there's a lot of steps here, but this is what we got to do for, and then that's why I think that you're not going to get this type of question. Now we can add these two equations, okay? So let's add them. Let's add them just like that. We add them, and clearly when we know that 10 E minus and 10 E minus are on the opposite sides, cancel them both out. So we cancel them both out. Boom, boom, boom. Cancel those two out. Now we just write down whatever we have left. So we have 10 Br minus plus 2 Br03 minus plus 12H plus gives us 5, but it's going to be 6 Br2 because you can clearly see 5 plus 1 here. So 6 Br2 plus 6H2O. And this, ladies and gentlemen, is our final equation. Okay, so let's see if we are correct. Usually I am always correct, but okay, let's take this, copy that, and there we go. That's our equation that we have here now. Okay, if I paste my equation here, wait, why can't I just paste my, okay, you can clearly see that they are the same. What happened to my equation? Shit. Oh yeah, they are the same equation. 10 Br minus 10 Br minus 2 Br03 minus 2 Br03 minus 12H plus 12H plus 6Br2 and 6H2O. 6H2O. Now they added another step here. See, if you write this, it's good enough. But to make it even simpler, you can divide this whole thing by 2 to get this, which is just a simpler version of the above equation. Not a problem. This is good enough, okay? And again, I don't think they're gonna ask us questions like this in the SAT, but it's good for you guys to know. So let me get over this whole thing again. If we want to balance oxygens, we add H2Os, and after we add H2Os accordingly with, like, the number of oxygens, we add the number of H pluses back over here, and then after we do that, we check out the charges, and then we balance the charges, and after we balance the charges, then we add the equations, then we make sure the electrons are the same, and then if they're not the same, we multiply any equation. We multiply one equation to fit our needs, or we multiply both of our equations to fit the needs. We basically want the number of electrons to be the same. They should be equal. After we get that, you add them, cancel the electrons out, get the equation that we deserve, and then if you want, you can simplify it by dividing the whole thing by one number, either 3, either 2, either 5, whatever the number may be, and you get the final equation. Okay, that was that. I hope that was a good explanation. I hope you understood. Okay, thank you. Okay, I'm back. This one, I'm just shooting this in the LC. So if it's a bit noisy, I'm sorry. Over here we have this formula for standard Gibbs energy, free energy. This is a simple formula. If I just remember this, and that's, you just have to plug it in, they're going to give you the values. They're usually going to ask you this value, and E naught cell, as I said, is equal to E cathode minus E anode, and that's how you find E that. F is 96,500 joules, okay? And then N is the value that most people get confused in. Let's look at this, okay? For this reaction over here, we can see that Cl is it's gaining an electron, basically getting reduced. So getting reduced means it's going to be cathode. Let's write the cell notation for this guy. Cl is getting reduced, so it's going to be on the reduction side, and Br is going to oxidize. So 2Br minus slash Br2 slash Cl2 slash 2Cl minus. This is the cell notation of this thing. On the left, we have our anode oxidation part. Over here, we have cathode reduction part. Okay, and then yeah, this is that. We can see now what we do for the n is for finding out the n. We see this side. Okay, we see that two electrons, 2 minus, are being gained. No, are being lost. Two electrons are being lost, and over here, two electrons are being gained. Over here, plus minus two electrons, and we have plus two electrons. Okay, now if the values of the electrons being lost and gained are the same, then that number will be considered n. Okay, but let's say, for example, see, this is for example only. Okay, this is not actually a real thing, but for example, I'm saying getting oxidized, so you want it to lose electrons, so plus 3 slash Cl. This is not an actual thing. Okay, so I'm just making this just for the example's sake. Then you get a Cl minus. So over here you can see that over here we can see the Na loses 3 electrons, minus 3 electrons to become 3 plus, and over here Cl gains 1 electron to become gains 1 electron. So now you can see that it's unequal. The number of electrons gained and lost is unequal over here. So what do you do then? In those cases, you multiply these two numbers to get your n. So it would be 3 into 1, which is 3. So your n would be 3. Let's say for the same example, let's say it was 2 minus. So it would be 2 electrons lost and gained. They're still different, okay? If they're unequal, then you multiply 3 times 2, which is equal to 6. So your n would be 6. Understand? That's how you find your n. Over here, as you can see, as I explained, that there are 2 electrons being lost and 2 electrons being gained. So over here, n is 2. And see over here, they're using the kilojoules value. That's why it's 96.5 only. Otherwise, it's 96,500. Okay. So yeah, and this is E cell, but E cell they're using the formula over here to calculate it. Or what we could have done is just use the values of E cathode and E anode, but as you can see, it's not given over here. If it's not given, you can use this formula to find out E cell. If the values are given of E, whatever, ECl2 slash Cl minus and EBr2 Br minus, then you can just use at E cathode minus E anode and find the formula, find the answer. But now that's that. Exercises, guys, these are pretty simple. You should know these by yourself if you listened and concentrated. But if by mistake I had any gaps in my knowledge and you couldn't understand some concepts and you don't know a few of these answers, please feel free to ask me in the comments or like message me on Instagram. That's my Instagram at. That's an underscore. Yeah, that's my Instagram. If you want, just message me there and ask me the question. And also, if you find any mistakes in my video, let me know by Instagram. Let me know that I made this mistake so I can correct it. Okay. Thank you very much.